Hey guys, my name is HRITOBROTO and today I'll be talking about file system implementation in operating systems. So first thing that comes into our mind when we think about files is where do we store it? So hard disks have two important properties that make them suitable for secondary storage of files in file systems. Blocks of data that can be rewritten in place, and they have direct access, allowing block of data to be accessed with only minor movements of the disk heads and rotational latency. Now, rotational latency, also called the rotational delay or just latency, is the delay time for the rotation of the disk to bring the required disk sector under the read-write head. It also depends on the rotational speed of the disk, which is actually called the spindle motor, and it is measured in revolutions per minute. So disks are usually accessed in physical blocks rather than a byte at a time. Block sizes may range from 512 bytes to 4000 bytes or even larger. File systems generally organize storage on disk drives and can be viewed as a layered design. The layered approach to file system means that much of the code can be used uniformly for a wide variety of different file systems, and only certain layers need to have the specific unit. Common file systems in the Unix file system are UFS, Berkeley, Fast File System, FFS, Windows System FAT, FAT32, NTFS, CD-ROM systems, ISO 9660, etc. Now, at the lowest level are the physical devices consisting of magnetic media, motors, and controls, and the electronics connected to them are controlling them. Modern disks put more and more of the electronic controls directly on the disk drive itself, leaving relatively little work for the disk controller card to perform. The I/O control consists of device drivers, special software programs which is often written in assembly language, which communicate with the devices by reading and writing special codes directly to and from memory addresses corresponding to the controller's card registers. Each controller card or device on a system has a different set of addresses, which is the register, also known as the ports, that it listens to, and a unique set of commands, codes, and results that it understands. The basic file system level works directly with the device drivers in terms of retrieving and storing raw blocks of data, without any consideration for what's in each block depending on the system. Blocks may be referred to with a single block number, for example hash 234234, or with head sector cylinder combinations. Next, we have the file organization module, which knows about the files and their logical blocks and how they map to physical blocks on the disk. In addition to translating from logical to physical blocks, the file organization module also maintains the list of free blocks and allocates free blocks to files as needed. Next, we have the logical file system, which deals with all of the metadata associated with the file, the UID, the GID, the mode, dates, etc. That is, everything about the file except the data itself. This level manages the directory structure and mapping of file names to file control blocks or FCBs, which contain all of the metadata as well as block number information for finding the data on the disk. So file system stores several important data structures on the disk. A boot control block per volume, also known as the boot blocks in Unix, or the partition boot sector in Windows, contains information about how to boot the system off to the disk. This will generally be the first sector of the volume if there is a bootable system loaded on that volume, or the block will be left vacant otherwise. A volume control block, also known as the master file table in Unix, or the super block in Windows, which contains information such as the partition table, number of blocks on each file system, and pointers to free blocks and free FCV blocks. A directory structure per file system containing file names and pointers to corresponding FCVs. Unix uses inode numbers and NTFS uses a master file table. The file control block or FCB containing details about ownership, size, permissions, dates, etc. Unix stores this information in inodes and NTFS in the master file table as a relational database structure. There are also several key data structures stored in the memory and in-memory mount table and in-memory directory cache of recently accessed directory information, a system-wide open file table containing a copy of the FCB for every currently open file in the system as well as some other relatable information, a per access open file table containing a pointer to the system open file table as some other information. For example, The current file position pointer may be either here or in the system file table, depending on the implementation and whether the file is being shared or not. So looking at this figure, this illustrates some of the interactions of the file system components when files are created and or used. When a new file is created, a new FCB is allocated and filled out with important information regarding the new file. The appropriate directory is modified with the new file name and the FCB information. When a file is accessed during a program, the open system call reads in the FCB information from the disk and stores it in the system-wide open file table. An entry is added to the per process open file table referencing the system-wide table, and an index into the per process table is returned by the open system call. Unix refers to this index as a file descriptor and Windows refer to it as file handler. If another process already has a file open when a new request comes in for the same file and it is shareable, then a counter in the same white table is incremented and the per process table is adjusted to point to the existing entry in the system wide table. When a file is closed, the per process table entry is freed and the counter in the system wide table is decremented. If that counter reaches 0, then the system wide table is also freed. Any data that is currently stored in memory cache for this file is written out of the disk if necessary. Next we have the partitions and mounting. Physical disks are commonly divided into smaller units called partitions. They can also be combined into larger units, but that is most commonly done for RAID installations. Partitions can either be used as raw devices with no structure imposed upon them, or they can be formatted to hold a file system. Raw partitions are generally used for swap space and may also be used for certain programs such as database that choose to manage their own disk storage system. Partitions containing file systems can generally only be accessed using the file system structure by ordinary users, but can often be accessed as a raw device also by root. The boot block is accessed as part of a raw partition by the boot manager prior to any operating system being loaded. Modern boot programs understand multiple OSs and file system formats and can give the user a choice of which of the several available systems to boot. The root partition contains the OS kernel and at least the key portions of the OS needed to complete the boot process. At boot time, and the root partition is mounted, and control is transferred from boot program to kernel found there. Continuing with the boot process, additional file systems get mounted, adding their information into the appropriate mount table structure. As a part of the mounting process, the file systems may be checked for errors or inconsistencies, either because they are flagged as not having been closed properly the last time they were used or just for general principles. File systems may be mounted either automatically or manually. In Unix, a mount point is indicated by setting a flag in the in-memory copy of the inode, so all future references to that inode get redirected to the root directory of the mounted file system. So next up we have the virtual file system. The virtual file system or VFS provide a common interface to multiple different file system types. In addition, it also provides for unique identifier or vnode for file across the entire space, including across all file systems of different types. Unix inodes are uniquely only across a single file system and certainly do not carry across networked file systems. The VFS in Linux is based upon four key object types: the inode object representing an individual file, the file object representing an open file, the superblock object representing a file system, the directory object representing a directory entry. The Linux VFX provides a set of common functionalities for each file system, using function pointers accessed through a table. The same functionality is accessed through the same table position for all file system types, though the actual functions pointed to by the pointers may be file system specific. Common operations provided include open, read, write, and mmap system calls. Next, we come to the allocation methods. So the first one is the contiguous allocation. In contiguous allocation, it requires that all blocks of a file be kept together contiguously. Performance is very fast because reading successive blocks of the same file generally requires no movement of the disk heads, or at most one small step to the next adjacent cylinder. Storage allocation involves the same issues discussed earlier for the allocation of contiguous blocks of memory. The distinction is that high time penalty required for moving the disk heads from spot to spot may just justify the benefits of keeping files contiguously when possible. Problems can arise when files grow or if the exact size of a file is unknown at creation time. Overestimation of the file's final size increases external fragmentation and wastes disk space. Underestimation may require that a file be moved or a process be aborted if the file grows beyond its originally allocated space. If a file grows slowly across a period of time and the total final space must be allocated initially, then a lot of space becomes unusable before the file fills the space. A variation is to allocate file space in large contiguous chunks called extents. When a file outgrows its original extent, then an additional one is allocated. For example, an extent may be the size of a complete track of even cylinder aligned on an appropriate track or cylinder boundary. The high-performance file system Veritas uses extents to optimize performance. Next, we have the linked allocation. Disk files can be stored as linked lists with the expense of the storage space consumed by each link. For example, a block may be 500 bytes instead of 512 bytes. Linked allocation involves no external fragmentation, does not require any pre-known file sizes, and allows files to grow dynamically at any time. Unfortunately, linked allocation is only efficient for sequential access files, as random access requires starting at the beginning of the file for each new location access. Allocating clusters of blocks reduces the space wasted by pointers at the cost of internal fragmentation. Another big problem with the linked allocation is reliability if a pointer is lost or damaged. W linked lists provide some protection at the cost of additional overhead and wasted space. Next, we have the file allocation table or the FAT. The file allocation table, also known as FAT, is used by the DOS in variation of linked allocation, where all the links are stored in a separate table at the beginning of the disk. The benefit of this approach is that the FAT table can be cached in memory, greatly improving the random access speeds. Next, we have the indexed allocation. The indexed allocation combines all of the indexes for accessing each file into a common block for that file, as opposed to spreading them all over the disk or storing them in a FAT table. Some disk space is wasted related to linked lists or FAT tables, because an entire index block must be allocated for each file, regardless of how many data blocks the file contains. This leads to questions of how big the index block should be and how it should be implemented. There are several approaches. The linked scheme is the first one. An index block is one disk block, which can be read and written in a single disk operation. The first index block contains some header information, the first n block addresses, and if necessary, a pointer to additional link index blocks. In multi-level index, the first index block contains a set of pointers to secondary index blocks, which in turn contain pointers to the actual data blocks. Combined scheme is the scheme used in Unix inodes, in which the first 12 or so data block pointers are stored directly in the inode, and then singly, doubly, and triply indirect pointers provide access to more data blocks as needed. Efficiency and performance. So, in Unix pre-allocates inodes, which occupy space even before files are created. Unix also distributes inodes across the disk and tries to store data files near the inode to reduce the distance of disk seeks between the inodes and the data. Some systems use variable size clusters depending on the file size. The more data that is stored in a directory, the more often the directory blocks have to be rewritten. As technology advances, addressing schemes have had to grow as well. Sun's ZFS file system uses 128-bit pointers which should theoretically never need to be expanded. Kernel table sizes used to be fixed and could only be changed by rebuilding the kernels. Modern tables are dynamically allocated, but that requires more complicated algorithms for accessing them. Coming to performance, disk controllers generally include the onboard caching. When a seek is requested, the heads are moved into place and then an entire block is read, starting from whatever sector is currently under the heads. The requested sector is returned and the unrequested portion of the track is cached in the disk's electronics. Some operating system caches Disk blocks they expect to need gain in a buffer cache. A page cache connected to the virtual memory system is actually more efficient as memory addresses do not need to be converted to disk block addresses and back again. Some systems, for example Solaris, Linux, Windows 2000, NT, and XP, use page caching for both process pages and file data in a unified virtual memory. Page replacement strategies can be complicated with a unified cache as one needs to decide whether to replace process or file pages and how many pages to guarantee to each of the category of pages. Solaris, for example, has gone through many variations resulting in priority paging, giving process pages priority over the I/O pages and setting limits to that neither can knock the other completely out of memory. I hope this video was helpful and that it cleared the concepts regarding system file implementation in operating systems. Thank you.